conclusions. And in the last, we'll briefly introduce the ongoing mission, the bipolar mission to Mercury. Okay, so let's start from introduce the flux transfer events. So on the right-hand side, so the top panel figure shows the very first measurement of flux transfer event, which is near the Earth's day-side magnetopoles. So in this presentation here, we focus on the flux groups. That is the core of the flux transfer event. The flux transfer event contains bipolar signature in the normal magnetic field component. That's shown here in this panel, the bipolar signature. And in the center, since it is flux group, so it contains enhancement in the total magnetic field. And frequently, in the center, inside the flux transfer event, we could observe the hot particles, which could be the reconnection accelerated particle or the magnetospheric particles. There are several models on the generation of flux transfer events. For example, the multiple X-line reconnection is normally required to generate flux transfer events. There are two multiple X-line reconnection model. One is the simultaneous X-line model that was proposed by Li and Fu in 1985, and also the sequential X-line reconnection models, which is proposed by Reader 2006. So in the Earth's magnetosphere, I think there are evidence for both models, and we will not focus on the model here. And in the Earth's study, the generation of flux transfer events normally require large magnetic shear angle. That is the southward interplanetary magnetic field. And because the magnetic field in the flux transfer events are open magnetic field lines, as shown here, that it has one end connect to the solvent and the other to the magnetospheric magnetic field. So the solvent particle could transport along the magnetic field and enter into the magnetosphere. And on the other hand, so the magnetosphere plasma could also transport along the open magnetic field line and leak out of the magnetosphere. Since in the core, it has a flux group, so flux transfer event could also transport magnetic flux from the day side magnetosphere to the night side magnetosphere, and then contribute to the flux circulation in the magnetosphere. For the case at Earth, a single flux transfer event could transport 4 megawatt magnetic flux, which compared to the total open magnetic flux, it is 600 megawatt. So that's really small. Okay. And this page here introduces the planet magnetic field in the solar system. So we have 8 planets in the solar system, and 6 of them, as far as we know, have global intrinsic magnetic field. That is Mercury, Earth, Jupiter, and Saturn, Uranus, and Neptune. Mercury is the innermost planet in the solar system. So it's in here. And so about them, I have shown the number. This number are the equatorial magnetic field intensity, which normalize to that of Earth. So as you can see, the magnetic field intensity of Mercury is only around 1% of the Earth's magnetic field intensity near the equatorial plane. So it is very small magnetic dipole. And the polarity of the magnetic table of Mercury is the same as the Earth's dipole. The Jupiter, Saturn, and Uranus and Neptune, they have much larger magnetic field comparing to the Earth. And Venus, Mars does not have global intrinsic magnetic field. And we know Mars has some strong crossover magnetic field on the south hemisphere. And Venus and Mars, they have highly conducting ionosphere which interact with the solar wind and form what we call the induced magnetosphere. Okay. So there are observations of flux transfer events in other planetary magnetospheres. For example, we show here on the left-hand side, it is an observation of flux transfer events on Jupiter's daytime magnetosphere. And on the right-hand side, it shows an evidence of flux transfer events at Saturn's magnetosphere. It's similar to the Earth. So those flux transfer events are normally separated by around 10 minutes, and it requires the magnetic shear angle, that is the magnetic shear angle across the daytime magnetic poles, to be larger than 90 degrees to occur. Okay, so here in this table, just summarize the flux transfer events impact on the magnetospheric dynamics. So on the first column, it shows the planet. As now we have introduced Earth, Saturn, and Jupiter. So and then the second is the magnetic flux that carried by each FTE. So they carried similar amount of magnetic flux. And the third column shows the polar cap flux. And Earth is the smallest, and Saturn and Jupiter are much higher. And the fourth panel here, this column here shows the percentage that the amount of magnetic flux that opened by each FDE. So as you can see, it's quite small. And with the repetition, and the fifth panel here shows the repetition rates. That is the separation time between neighboring flux transfer events. So they were on the order of minutes, and we can estimate the potential voltage that contributed by each FTE to the magnetospheric voltage, cross magnetospheric voltage, and according to this equation here. So we can get a value like they contribute like between 1 to 10 kilovolt. That is very small comparing to the cross magnetospheric potential like at Earth, at Jupiter, and Saturn. Okay. So here, just briefly introduce the solar wind radial variations in the solar system. The horizontal line, the horizontal axis shows the radial distance to the sun. It's in the unit of AU. And the vertical here is 3 lines. The green line shows the solar wind dynamic pressure, and the red line shows the solar wind plasma beta, and a black line shows the solar wind arsenic Mach number. And the place of each planet represented by the vertical dashed lines. So in the innermost place is the Mercury here, and the Earth is here, and this is the Jupiter, and this is the Saturn. Comparing to the solar wind properties that near the Earth's orbit, we can see that near Mercury's orbit, the solar wind dynamic pressure, which represented by the green line here, is much higher. That's around 50% higher than the Earth's orbit, the dynamic pressure. And the solar wind plasma beta and also the arsenic Mach number is only around half of the values near the Earth's orbit. So it's really a great place to investigate how those low arsenic Mach number and the low solvent plasma beta influence the day-side magnetopause reconnection and then influence the solvent magnetosphere interactions. Okay, so let's move to the next part, Mercury's magnetic field and magnetosphere. So in the previous page, we have introduced that Mercury contains a small dipole comparing to Earth's dipole. And Mercury is embedded in a much stronger solvent comparing to Earth. So as a result, the interaction between the solvent and the Mercury magnetic field form a miniature magnetosphere, what we call a miniature magnetosphere comparing to the Earth's magnetosphere. Although small, but Mercury's magnetosphere can hold off the constantly high streaming solar wind from directly hitting the planet's surface during most of the time. So on the right hand side here, we show a snapshot of a global Hall MHD simulation. So this figure is provided by Xinzhi Jia and Changkun Li. They both work on the U of M Buttress model. And so here, this region here, this is the magnetopause. So as you can see, the magnetopause was only around like 100 kilometers above the planet's surface. We know at Earth, the subsolar magnetopause distance is normally larger than 10 Earth RE. That is more than 60,000 kilometers above Earth's surface. So that's quite small. So this is quite tiny magnetosphere comparing to the Earth's magnetosphere. So another point that we need to be aware is that Mercury does not have a significant atmosphere. It only has an exosphere, and that exosphere is tenuous and it's not conducting, almost collisionless. So that the particles inside the exosphere would rather collide with the planet's surface, but not to themselves. And the most abundant species, heavy ion species in the exosphere is the sodium, neutral sodium, and sodium ions. So therefore, on the right-hand side here, we show two FTEs. And the FTEs, they contain the open magnetic field lines. And one end of the open magnetic field line connect to the solar wind. And the solar wind hard particle, high flux particles would transport along the open magnetic field line and enter into the magnetosphere and impact on the planet's surface and neath the cusps, which would sparging, which we would call sparging, what we call sparging those materials near the regulus, the planet's surface, and out of the planet and feed the exosphere. Okay, so this coupling is quite different from what the solar wind ionosphere or atmosphere coupling. What we call is solar wind surface coupling. Okay, so this here figure here, we show the data we are using in this presentation. So we use the messenger measurements. Messenger measurement is the second spacecraft that visited Mercury. The first one was in 1970s, Miranda 10, also a NASA mission. Messenger was launched at August 3rd, 2004, and MESSENGER orbited Mercury from March 18, 2011 to April 30, 2015. So MESSENGER provided more than 4 years, 4 year Earth years measurements of Mercury's magnetosphere, which correspond, the 4 Earth year correspond to more than 16 Mercury years data. The measurements we are using is 2. One is the magnetometer, which provided magnetic field vector in a sampling rate of 20 vector per second. And then the second is what is the fast imaging particle spectrometer, the FAPS, which provided measurement of ion species in 10 seconds, in the resolution of 10 seconds, with energies below 13 keV. So on the right-hand side here, it shows the orbit of the trajectory of MESSENGER when it orbited Mercury. So it has parabasis of several hundred kilometers above the planet's surface near the northern pole region. And when it crossed the day-side magnetosphere, it crossed sometimes very close to the subsolar point and then the northern cusp. So it could cross from the day side to the night side. On the other hand, it's also crossed from the night side to the day side. So it depends on the season. Okay, so let's move to the result that we have here. So the first subject that we want to discuss is the FT shower, which I will introduce later, and their dependencies on magnetic shear angle and the magnetoshear's plasma beta. Okay, here we show a day-side magnetosphere crossing made by MESSENGER on 2012. So this figure includes a duration of around 20 minutes. So from the beginning to the end, it is around 20 minutes. In this figure here, MESSENGER crossed the subsolar magnetosphere near the subsolar magnetosphere, and it moved from the magnetosphere into the magnetosphere. This is highlighted to the magnetosphere region, and then it crossed the northern cusp and to the night side magnetosphere. So in each panel, the first panel shows the proton measurements, and the second shows the sodium ion spectrum, and the third is the observed density of sodium ions. And this is the BX measurements, the BY and BZ, and the magnetic field intensity. Okay, near the subsolar magnetosphere here, there are large number of flux transfer events. So as I mentioned earlier, this figure is only have a duration around 20 minutes. And near the subsolar magnetosphere here, in around 5 minutes, we observed 40 flux transfer events. So the flux transfer events appear in large number and high frequency, and they are only separated by a few seconds. So we term these flux transfer events are the flux transfer event shower. And in these flux transfer events, and in the day-side magnetosphere, as shown here in this panel, this is the BZ component. And remember, Mercury is in the same polarity as the Earth's. Mercury's dipole is in the same polarity as the Earth's dipole. In the magnetosphere, the BZ is southward. So it is a large magnetic shear angle event, which has an angle of around 120 degrees. But at the same time, on the two sides of the dayside magnetic poles, as shown here in the last panel, that is the magnetic field intensity. We barely see the intensity change on the two sides of the magnetic poles, which indicate that here there is a strong plasma depletion layer that correspond to very low plasma beta in the magnetosphere. So remember, at Mercury's orbit, the solar wind alpha Mach number is small. Therefore, the plasma depletion layer is a quite common phenomena on the day side of Mercury's magnetopoles. Okay. So near the subsolar magnetopoles here, we store large number of flux transfer events. That is a flux transfer event shower, what we call flux transfer event shower. And on the day side magnetosphere here, which is high latitude magnetosphere, on the first panel, you see the several intermittently appeared low energy, high flux particle, which should be the injected solar wind particles associated with the flux transfer event. At the same time, in the cusp region, there are many depressions, magnetic depressions in the total magnetic field, in the intensity here. We call it plasma filament, which should correspond to the injected solar wind particle, which diamagnetically decrease the magnetic field intensity and cause those magnetic depression in the cusp region. Okay, so in the day side magnetosphere near the magnetic poles at the same time, we observed a large number of sodium mines. The sodium mines are originated from the Mercury, from the planet. And during FT shower intervals, we did observe a large number of them. Okay, so let's move to another event here. So this event was taken from Sullivan et al. 2014, and this event was occurred during the northward interplanetary magnetic field condition. Okay, so the first panel here shows the proton spectrum, and the second panel here shows the observed density of sodium ions, mostly sodium ions, the yellow color. And the third panel shows the BZ component. And the last panel shows the magnetic field intensity. So in this event, Mercury crossed the cusp first, and then the high latitude magnetosphere, and crossed the dayside magnetic poles and enter into the magnetosphere. So in the opposite traveling direction at the last figure. And the vertical line here indicates the dayside magnetic poles. And what we observe in the magnetosphere, the magnetic field is northward. And we calculated that we found the shear angle is around 70 degrees. But near the dayside magnetic poles here, we also see large number of flux transfer events. And in the cusp region or in the dayside magnetosphere here, there are large number of FTE related solar wind FTE related solar wind particles. So those should related to the injection, caused by the injection of the flux transfer events. And almost no magnetic field change across the magnetic poles, which indicated that still a thick plasma depletion layer exists on the day side, ahead of the dayside magnetic poles. And the plasma beta in the magnetosphere is also very small. That is around 0.06. So from these two cases, one a southward interplanetary magnetic field, this one a northward interplanetary magnetic field. Both observed large number of flux transfer events, and it seems the interplanetary magnetic field polarity, which corresponds to the magnetic shear angle across the daytime magnetopoles, is less important as long as you have a magnetochase that is with very low plasma beta. So we don't know. It seems plasma beta play an important role. Therefore, we decide to do a statistical research over the entire messenger database. As we showed before, we have more than 4 Earth years, that is 16 Mercury years measurements. So we have surveyed the entire messenger region, and we found 3,748 daytime magnetopole crossings. And then we apply a machine learning algorithm to automatically identify those flux transfer event type flux groups. So the machine learning algorithm was developed by Andy Smith from MSSL UCL, and the publication could be found here. And we defined those daytime magnetopole crossings, which were accompanied by more than 10 flux groups, the FT shower. And we found that around 2,000 of the daytime magnetopole crossings, that is around half of them, contained FT showers. So this is really in very high occurrence rate. And in the next, we arrange the occurrence of the FT showers according to the magnetic shear angle across the magnetopoles and the magnetochase plasma beta. So if you want more information of how we identify the flux transfer event, you can find them in our last year publication. So okay, let's move to the result here. So this figure, the horizontal axis shows the magnetic shear angle across the daytime magnetopoles for the event, and the vertical line here is approximately the magnetochase plasma beta, which is determined from the pressure balance based on the assumption the pressure balance across daytime magnetopoles. And the color shows the occurrence of FT showers in each beam. What we see here, we show clear magnetic shear angle dependence. Like indicated by this blue arrow, the larger the magnetic shear angle, the higher the occurrence of the FT shower. At the same time, especially in the large magnetic shear angle region here, we also see clear magnetochase plasma beta dependence. That is, the lower the magnetochase plasma beta, the higher the occurrence rate, the occurrence of FT showers. One thing that we need to note is that even with a very low, very small magnetic shear angle, as shown here, that is around 70-degree magnetic shear angle, the occurrence of the FT shower is very high, more than 70%. It also need to note that in a previous study, Lisa et al., they show a similar shear angle dependence, but they did not investigate the plasma beta dependence. Okay, and in the following, we have shown the fluxual properties. That is the duration, the fluxual duration, the spacing, that is the time duration between time separation between neighboring flux transfer events, and the maximum magnetic field intensity inside the flux group, and the amount of magnetic flux carried by each FTE. they are dependent according to the magnetic shear angle. The horizontal is the magnetic shear angle. You can see that the duration increased with increasing magnetic shear angle, and the spacing, that is time separation, decreased with increasing magnetic shear angle. And while the magnetic field intensity and the amount of magnetic flux does not show clear dependent on the magnetic shear angle. Okay, in here we also investigate those properties depend on the magnetosphere plasma beta. Again, the first line, the first panel, the duration, and then spacing, and the maximum magnetic field intensity, and the amount of magnetic flux of each FTE. We show that the duration increased with increasing plasma beta, magnetosphere plasma beta. The spacing, the maximum magnetic field intensity, and the amount of magnetic flux decreased with increasing magnetosphere plasma beta. So with the spacing of the flux transfer events and with the amount of magnetic flux in each FTE, so we can estimate the potential drop associated with each individual FTE. And we got a value like 6 to 9 kilovolt. And here we have put Mercury into the table that previously introduced. So this line here, the red shows the Mercury's FTE properties. So the magnetic flux carried by each FTE is around 0.04. It could be higher, it could be lower. And the polar cap potential is like 2.6 MW. And the percentage opened by each FTE is around 3 to 5%. And this is larger comparing to other planetary magnetospheres, which the FTEs during the FTE shower has a repetition rate of around 5 seconds. So we got a potential drop that's like 6 to 9 kilovolt. And the Mercury's magnetosphere, it has a cross magnetosphere potential drop. It's like 16 to 20 kilovolt. So that means each FTE could contribute to like 40% of this cross magnetosphere potential drop. So FTEs play a relatively important role on Mercury's magnetosphere. Okay, so that's the first one. And the second topic that I wanted to discuss is the flux transport associated with the flux transfer events. So from the Earth study, we have two models of flux transport. The first model is a single X-line reconnection model, as shown here, was proposed by Weijie in 1961. So in this model, a single X-line occur near the day side subsolar magnetic poles, and it keep on reconnecting and transport open magnetic flux from the day side to the night side. That is a single X-line reconnection model. And later, Li and Fu, they proposed the multiple X-line reconnection. So the multiple X-line reconnection, it generates flux transfer event between neighboring X-lines. And as you hear, the flux transfer event could also transport the magnetic flux from the day side to the night side. So there have been many studies on how large amount of magnetic flux that have been transported by flux transfer events in the Earth's magnetosphere. I think most of the studies show that the multiple X-line reconnection flux transfer event transport only less than 5% of the flux for the flux circulation during the Dengli cycle in Earth's magnetosphere. Since we have the database, we estimated the flux transfer event contribution to Mercury's Dengli cycle during the flux transfer event shower interval. So we have calculated the amount of the magnetic flux carried by FTEs during Mercury's Stirling cycle. And the value here is shown the dots in the two figures. And the two figures, the difference are the Magnetosphere plasma beta and the magnetic shear angle. That's the difference between the two. And in each figure here, the horizontal dashed line shows the loaded magnetic flux in the tail lobe during Mercury's Stirling cycle. As you can see, FTE could transport, I think, majority of the magnetic flux that required for the open flux during Mercury Stirling cycle. It shows magnetic shear angle dependence. That is the lower magnetic shear angle, the amount of magnetic flux transported like 60%, and the higher magnetic shear angle, the amount of magnetic flux was transported like 80%, 85%. And it does not show clear Magnetospheric plasma beta dependence. That is around 80% of the magnetic flux will be transported by flux transfer events during Mercury Stirling cycle. So from this figure here, we can obtain 2 points. First, multiple X-line reconnection could transport majority of the magnetic flux for Mercury's flux circulation during the Stirling cycle. And second, the result indicate that multiple X-line reconnection model is probably the primary reconnection model on Mercury's magnetosphere. Okay, so let's move to the last topic that I want to discuss. So how the FT shower, the particle transport, and how they influence the exosphere influence Mercury's exosphere. Okay, so first thing is briefly introduce the loss count. I think everybody is familiar with the loss count. Loss count indicates the picture within the loss count, the particles will be lost. For the Earth's magnetosphere, the particle will precipitate into the upper atmosphere. For Mercury, it will precipitate into the planet's surface. So how we calculate the loss count? Here shows the equation here. So we know the magnetic field intensity near the equatorial plane, and we know the magnetic field intensity near the planet's surface. We can get the loss count. And we make a simple estimation for our case. So we got a value inside the flux transfer events, the magnetic field intensity inside the flux transfer events, which should replace the equatorial magnetic field intensity. And we know the magnetic field intensity near the planet's surface. And we calculate the loss count distribution over the north hemisphere of Mercury's planet. And the dashed elliptical circle here indicates approximately the cusp region. And we can see that the loss count inside the cusp is around 50 degrees. That is huge comparing to what we know at Earth. So the loss count in Earth's magnetosphere is like a few degrees, 1 to 3 degrees. And it's even smaller for the magnetosphere of giant planets. Okay, so we know that during the FT shower intervals, there are large amount of FTEs. So it could also bring large amount of solar wind particles into Mercury's magnetosphere and precipitate it into the cusp region. So we want to know how those particles could influence Mercury's exosphere. So in our previous study, we have investigated over the entire messenger mission. We have got around 2,000 FT shower intervals and 2,000 non-FT shower intervals. So we divided them into 2 intervals. And the left shows the non-FT shower intervals and the right shows the FT shower intervals. And the color indicates the average sodium ion density. So remember, sodium ion is one is the most abundant heavy ions in Mercury's exosphere. And the white line is the average magnetic field lines, which is derived from the measurement of the magnetic field during each intervals. What we can see from these two figures, the sodium ions clearly enhanced during FT shower intervals. And at the same time, we see that during FT shower interval, there is an entry layer, as shown here. You see the magnetic field line. This is the open magnetic field line, and the sodium ions are mostly concentrated in the entry layer. We have estimated the sodium ion density. We got a transport rate like 6.0 times 10 to the 23rd per second. And this value actually is a lower limit because we don't have measurement in higher altitude region. And this value is comparable to the neutral sodium tail, the escaping rate based on the ground-based telescope of Mercury's neutral sodium tail. So it's really a huge number of sodium ions in this entry layer here. So in this figure here, we investigate the properties of the solvent proton particles and the sodium ions. We want to show where those sodium ions come from and how the solvent particle look like in the entry layer here. So we trace the measurements inside the entry layer here. And from the shoulder, we term them the start point, the shoulder, and the footprint of the entry layer. So if we see the density profile here, so the horizontal is the density, and the vertical is the average magnetic field intensity in each point. And the highest value here corresponds to the planet's surface. And what we see here is that the sodium, you see the solvent proton density increase as the magnetic field intensity increase. So which means the plasma content conserved inside the solvent entry layer. And we got a value like 6 to 5 per cubic centimeter. And we can estimate the precipitation rate associated with the entry layer. And that value is around 10 to 25th per second. And a previous study based on the average precipitation rate over Mercury's North cusp is around 10 to the 24th per second. So this value is around an order of magnitude higher than those average value. And the Poe et al. They investigate the cusp filament, which actually correspond to the active period of Mercury's magnetosphere. And they got a comparable value as this study. But the sodium ion here, they exhibit the very different changes comparing to the solvent protons. So the density decreased as they getting approach to the planet's surface. So they must come from a different source. And here we believe they are continuously generated. So the solvent particle move along the entry layer, and eventually they spatter on the planet's surface and spatter out those neutral sodium and sodium ions out of the planet's surface. And then when they move up to a certain altitude, they will feel the solvent convection electric field. And the solvent convection electric field will push them back. So therefore, you will see accumulated sodium density in certain altitude, and the density should decrease along the with the decrease of the altitude. Okay, so here come to the conclusion here. So in this presentation, we have discussed the occurrence of the FT shower. We show clear magnetic shear angle dependence and also plasma beta dependence. And we also show that FT can transport energetic solvent particles into the cusp. And FTE could account most of the magnetic flux circulation in Mercury Dunkley cycle. And also we see that the flux transfer events form a solvent entry layer. The solid ions are significantly enhanced in solvent entry layer. And we believe this result confirm the hypothesis that Magnetosphere reconnection modulate solvent impact on the surface, which spatters sodium ions into the surface bounded exosphere. And in the end, I just want to briefly introduce the Babin-Colombo measurement. Babin-Colombo measurement is the ESA and JAXA joint measurement. It was launched on October 20, 2018, and it's on its way to the planet Mercury. It still haven't reached planet Mercury. So last year, 2020, it's only flyby of Earth, and the first flyby of Venus. And the coming August, it will have the second Venus flyby, and October it will have the first Mercury flyby. And after around 6 Mercury flyby, it planned to enter the orbit of Mercury at late 2025. And the first set of data should be available the spring 2026. And the Mercury, the Babin-Colombo measurement contain two satellite spacecraft. One is the MPO, as he show here, the blue line at a lower altitude orbit, which is built by ESA. And the other is MMO, the Mercury Magnetosphere Orbiter, which is designed to investigate the magnetospheric dynamic of Mercury's magnetosphere. And MMO carries comprehensive measurement of the field, plasma, and even neutrals. So by that time, very importantly, we can have a solvent monitor when we investigate those dynamics in Mercury's magnetosphere. Okay, that's all. Thank you for your listening. Kevin?
Thank you, Weijie. That was really great. What a fascinating magnetosphere. So I'll open it up to questions. I would personally like to sneak my question in first, though, since I currently have the floor. Weijie, would you mind going back to your plot there? You showed your delta beta versus magnetic shear angle.
Yeah.
Yeah, that's the plot. So that's really interesting. I mean, it seems like just at a glance here, it seems like there's a stronger dependence. Let me just get to my question here. I'm wondering how you calculated the shear angle and the delta beta. Are those at the Mercury location, or did you try and estimate delta beta and shear angle at like the subsolar point or wherever you expect the reconnection to be occurring?
Thank you. That's a really good question. So the magnetic shear angle is calculated based on the when messenger cross the magnetopoles, we have measurements in the magnetosphere, and in the daytime magnetosphere, we calculate the shear angle between the two. That's how we calculate magnetic shear angle. The plasma beta here, since we have limited plasma measurements, we assume pressure balance on the two sides of the magnetopoles. I think you made a good point. We did try to use a model to derive those measurements, messenger that not always cross near the subsolar magnetopole. Sometimes it's in the higher latitude, sometimes it's in the different magnetic latitude. magnetic longitude. We do try to use a model to derive those parameters back to the subsolar magnetic poles, and we found some very weird trend. So we decided to use the local parameter instead of those derived parameter. Yeah, but you made a very good point, though.
I see a hand raised here. I think you could just jump in if you have questions. Rebecca, I think you're muted. Yeah, there you go.
Sorry, I just realized that. That was a really nice talk, Weijie. Thank you very much. That was great.
Oh, thank you, Rebecca.
So yeah, just to follow up maybe on this question, the estimation of the plasma beta, so that was not from FIPS measurements, is that correct, for all of these events?
No, that was all derived from magnetic field measurements. Yeah.
Okay. So that's very similar to the way that I estimate the plasma ram pressure, for example.
Yeah.
Sorry, the dynamic pressure.
The dynamic pressure, yes.
Assuming a pressure balance.
Yeah.
Okay.
Yeah. Yeah.
And when you looked at all the FDs, it sounds like you used an automatic detection method. Did you check them by eye, at least some of them? I mean, I realize you didn't check all of them, but did you go through some of them that you agreed that these are really flux ropes? Sometimes these algorithms are not that accurate. So.
Thank you, Rebecca. That's a very good question. Yes. So I didn't show here. So because Andy Smith, he published his result on JGR, so I employed his method. But actually, I developed a set of code myself, and I compared my result with his result. So we agree with each other. So therefore, we published this result. I didn't publish a paper based on my I did not publish a paper of my algorithm because I think that is pretty enough. A lot of already have several studies, so I just use the results and publish a paper. Yeah.
Sure, that makes sense. I'm just wondering if you also check them by eye.
Yes.
In terms of
yes, I did. Yes, I did. When
okay, this
yeah.
agrees with what I would think a flux rope should look like.
Yeah. Okay. I did check by eye. I did not check all of them, but I did check 10 at least 10 magnetic pole crossings. I think it's quite precise, quite accurate. It's like it could identify most of the flux groups in my case. Yeah, and the identification were based on the properties of the flux groups. You need to require the magnetic rotation, in 30 angle in the hologram. So you require them, to be you feed them with an elliptical, and the angle should be larger than 180 and something like that. Yeah.
Right. Yeah. I mean, I'm not sure. I haven't looked at your paper, but I will now. Whether you looked at the if you calculated a false positive and false negative rate from this, it would just be useful to have something like that with automatic codes like that, or automatic detection algorithms, I should say. And just one other quick question on, I think it was on slide 24, if you could jump to that.
This one?
24, not 4. That one looks like it's 14. Oh, yeah, 21, 24.
24.
Yeah, the lost cone one.
Okay, yeah.
So first of all, what was your estimate here for the planet's magnetic field strength on the surface? Is this from a recent model, or?
Oh, I use Dr. Haya code, his model.
Okay.
Yeah.
Yep. Yeah, I know, I'm familiar with that. Yeah, I just wanted to point out that in my 2014 paper, we have an actual measurement of the loss cone in the north cusp. That's an actual measurement from the magnetic field.
Oh, thank you.
So that's a combination of FIPS data and magnetic field data. So that's
oh, thank you, thank you. I did read a lot of your paper, but I did not pay too much attention to the 2014 paper. But I will check that out later. Thank you.
Sure. Yeah, no worries. That's around 60 degrees, so it's close. I think it's 59 degrees. What we measured. So
perfect.
Close to what you've got here, but anyway, that's just an actual measurement. So if you need that,
yeah, I will check that out. Thank you.
No
thank
worries.
Thank you, Rega.
Any other questions here? I have one more, if not. All right, well, Weijie, another question for you here is, so a lot of the plots and sort of cartoons you showed indicated closed field line reconnection at the low latitude magnetopause. And sort of, I gathered that you were suggesting that was sort of happening for even really low shear angles in northward IMF. Does Mercury's magnetosphere ever have open field line reconnection, sort of at the high latitude cusp region? Can both those happen simultaneously, or is it just sort of subsolar low latitude reconnection?
That's a really good question. So I think in previous study, there are reports on the open magnetic field line reconnection, but whether they could occur simultaneously, I don't know. I don't have the answer. That's a really good question. There's several reasons why we can't observe them now, because we don't have high enough resolution for particle measurements. I think that will require very high time resolution of particle, both time and spatial pitch angle resolution. Well, another thing is that we only have one spacecraft, so it's really difficult to determine, if there are reconnection on high latitude and then near the dayside magnetopause. So that's a really good question, but I don't have the answer.
Yeah, I know. I mean, I know one of the consequences is, open field line reconnection has a hand in generating the low latitude boundary layer.
Yeah. Yes.
Could be something to look for. Maybe though you need the high time resolution plasma measurements. Anyways, we're a bit past the hour here, so thank you, Weijie, again. Really interesting talk. You've given us a good start to our 2021 seminar series. So
thank you,
excellent.
Kevin.
Yeah, thank you very much.
Thank you, everybody. Bye-bye.
Bye.